Hey physics peeps, I just wanted to record a video for you to help get you started on Worksheet 2 from Unit 8 because this is something you will want to work on tomorrow in class when I'm gone, and it will be due by the end of the day next week on Monday. So here we go with just some helpful tips as we go through the problems. There's actually 3 different problems, and some of them are broken up into parts. But anyways, let's just kind of go through it all, and hopefully that'll be a good start for you. So the first problem here is this airplane that is flying in a circle, and the airplane is at the top of its circular path up there, and it's upside down. And in question 1A, it says, determine the value of the centripetal force acting on the woman flying in the airplane when at the top of the loop as indicated in figure 1. And then 1B says, construct a quantitative diagram of all relevant forces acting on the woman. And then 1C says, does the woman feel lighter or heavier than normal at this position? So I'm not going to go in to answer all of those questions, but I do want to help you get started. And whenever we have a centripetal force or a circular motion problem, we really want to get that force diagram written out before anything. So I actually want to draw that out, and hopefully that will give you some direction. So what I've done is I've drawn a picture of the pilot that is upside down, and the pilot is sitting on the seat, and so the seat is actually above the pilot. So we're looking at this picture of the stick figure, and while this pilot is sitting there in the chair at this point, the velocity of the pilot is straight forward, so there is a velocity arrow to the right, as you can see. And then because the pilot is at the top of its path, then there needs to be a net force, an extra amount of force pointed towards the center of the circle. And so that's why F net is pointed straight down. So that means we need to have, once again, extra force towards the center of the circle. So what is involved in that extra force? So let's draw a force diagram of this pilot sitting in this chair, this woman in this chair. So first off, I'm going to draw a dot right there, and from that dot, I'm going to draw the forces. So the first force I will draw is gravity, because gravity is going to be straight down, and so it's going to be the gravity on woman by Earth. So that one's easy enough. Now the one that is tricky is, okay, the seat is touching the woman, so which way is the seat pushing on the woman? Well, since the seat is below the woman's rear end, if you will, or actually above her rear end because she's upside down, that means the seat has to be pushing into her, which means the seat actually is pushing down as she is upside down. And so the seat provides an Fn force going down, Fn on woman by, we'll say, airplane seat. Now that should probably look really weird. You have this woman hanging upside down at the top of the airplane's flight. And while the woman is upside down at the top of the airplane's flight, she has 2 forces acting on her, and they're both pointed down. Well, to me, if I'm looking at that force diagram and you have only forces pointing down, that would make me think that the woman needs to fall straight down out of the chair. She would if the plane stopped its movement. But the plane is moving fast enough to the right. And while the woman is moving fast enough to the right, her motion continues to go to the right, and the plane then makes a motion that curves around, and so she flies into the curve. And so the seat actually just catches her as she goes around. So that's what happens. So yes, she wants to fall down, but her body's going forward, so her body moves into the seat as the seat makes that circular path. Okay, so when you do 1A, you really don't need the force diagram to do that, but you do have your net force that is pointed downwards, and that is the centripetal force. And so you just make the calculations based off of what you know right here. You know your R, you know your V, and you know your M, and you use your centripetal force equation, which is the F net equation for circular motion. Now, to construct a quantitative force diagram of all relevant forces acting on the woman basically just means you need to tell me what Fg is, and you need to tell me what Fn is. So up here in 1A, you're finding out what F net is, and then in 1B, you're trying to figure out what Fg and Fn is. And remember, F net is how much extra force you have pointed towards the center of the circle. And knowing that there's only two forces, and they're both pointed towards the center of the circle, the F net makes up those two forces, both Fg and Fn. They're both going in the same direction, so they're both going towards the center, so they're both positive. So you'll add them up. Now in 1C, does the woman feel lighter or heavier than normal at this position? So if you want to feel not lighter or not heavier, just feel like nothing's going on, then you would feel forces that are equal to your gravitational force. Now you'll end up feeling lighter if the forces around you are less than the gravitational force. And so the only other force that's acting on you is the Fn force. And so if that Fn force is less than Fg, then you will feel lighter. If that Fn force is bigger than Fg, then you'll feel heavier. All right, so let's go on to number 2. Number 2, I do want to start this one off with the force diagram because this is a really tricky one. So there is an amusement park ride. It has different names in different places, whether it's at a carnival or a county fair, or whether it's at an actual amusement park. But it's something that spins so fast that when it gets going, you actually feel like you're being pinned against the wall behind your back. And you get pinned so hard against that wall that you actually can float, where you won't fall down and the floor can fall away from you. And I'm hoping possibly you've experienced this ride, but if you haven't, that's what happens. So what I want to do is I want to draw a force diagram of this person as if they are right here. So they're pushed up against the wall right here. And when I do that, I've kind of got a side view here. So the back is against the wall, and when I draw the force diagram, I want to draw it in a way that's for this person right here on the side. If I draw it for this person that's at the back, it's going to be too tough to see, so we'll have to just look at it from the side. Because if we look at it at the back here, you're going to have to draw forces that come out of the paper or out of this screen, and you really can't do that. So now we're going to focus on this person right here that's on the side. So this person, because the wall is on the back of the person right there, that means the wall actually is pushing, in our case, to the left, into the back of the person, and that's a normal force. And that's the force that makes you feel like you're being pinned against the wall. So it's actually pushing in on you, and you feel that force on your back, and so it makes it feel like you're pinned against the wall. But actually what you're feeling is the force pushing on you and trying to push you towards the center of the circle, because when everything goes in a circle, the force is always pushing objects towards the center of the circle. So your body wants to keep going straight, but the wall keeps pushing against your back to keep you in circular motion. So you have that normal force pushing into your back. And then there is a force that is up. and there's also a force that is down, because what happens when you're going so fast, your body doesn't go up or down. It's in place. So you have to have equal forces going up and down. Well, the downward force is Fg, and the upward force is a force that doesn't allow you to slide down the wall, and so that's a friction force. So you actually have friction between the wall and your back that is keeping you sticky enough so you don't fall down the wall and slip down. So what you have now here is you have this force diagram where you have Fn going to the left, Ff going up, and Fg going down. And this is weird because we've always had friction on horizontal surfaces or maybe a ramp, so they've always been more horizontal. But in this case, we actually have a friction force going up and a normal force then going to the left. And you notice the normal force and the friction force are both perpendicular to each other. And so here we go. And so so the normal force is actually the force that's keeping us in a circular motion. And so that is the net force. So the net force due to centripetal forces is actually just the normal force that is pushing on your back. So then we will use that as the net force or the centripetal force in our calculations. So as we look at this problem, number 2 says, what is the maximum period of rotation necessary to keep the riders from sliding down the wall? So we're actually looking for this period, this t. And, a couple things to keep in mind here. We know that v is equal to 2 pi r over t. We know that F net is equal to mv squared over r. And we also know that Ff and Fg are equal to each other. And we also know that Ff is related to the normal force by the coefficient of friction times Fn. And you'll notice that you are given a lot of these things in this list right here, where r equals 1.5 meters, and mu, or the coefficient of friction, equals 0.50, and then m, which is the mass, equals 73 kilograms. So you can use all of these numbers here and all of these equations right here to end up solving for the period. And that's the work that I would like you to go through. You will pretty much fill up this whole space here because it is several different calculations. All right, so moving on to 3. 3 is an awesome problem because what it does is it combines circular motion and it combines energy. So we do have to take some of what we learned last unit and we'll have to apply it to this unit. And so, so when we're talking about energy, we're talking about the roller coaster car having some gravitational energy up here, and then we'll say that's our initial state. And then the roller coaster car will get right here at the top of the circle. We're going to care about that there. And when it gets to the top of the circle there, it's going to have two energies. It's going to have some EK, and that's going to be like EKF in the final state. And then it's also going to have some gravitational, so that'll be like some gravitational in the final state. And then the other part we'll care about is when this cart gets to the spring and it stops. And so the velocity becomes 0 at this point. And so at this point, we're left with just elastic energy because we're on the ground levels and we have no height and we're not moving anymore. And so this would be like another, final position. So we have gravitational at the beginning, that's initial, so that'd be like position 1. And then we have kinetic and gravitational in the middle here where it's at the top of the loop, and that would be like a second position. So we call those finals there. And then the last position, the third position, is some final elastic energy. So, so we have all that. So for number 3, it just says, what must the minimum speed of the car at the top of the loop be to ensure that it would not fall off the track? So it is going its absolute slowest so that it just makes it around the loop. And when it goes its absolute slowest just around the loop, that's when the track has to do nothing to push on it. If it goes any slower, the roller coaster car will fall straight to the ground. And if it goes any faster, then the track will start pushing on it with an FN force. But this is that minimum speed where FN goes bye-bye and the cart doesn't fall, and it just it just nicely goes around the ramp. And so that means the only force we would have at the top of the track is Fg. And so Fg is going to be equal to our Fnet. Now, let me write that better. So Fg will be equal to Fnet. And so then you'll just solve knowing what's in our list of things right there. Okay, and remember Fg is equal to 9.8 newtons per kilogram times mass. And I should have stated that previously up here. Fg is equal to 9.8 newtons per kilogram times your mass. Alrighty, so that's where we are on 3. And number 4, it says, what must be the minimum initial height to ensure that the car would not fall off the track? So what height do we need to have up here so that it's going fast enough down here to be able to go around the track? Okay, so we do take what our speed is here, and we can now put this speed, whatever we find here, we can put it into our kinetic energy there. And then we can also put in this height into that gravitational potential energy there. And so we can figure out how much of these energies total we have. And once we know the total energy of this kinetic plus this gravitational, we can know that it is equal to the initial gravitational potential energy. And so then we can find what this H is right there. Okay, and then number 5 just says, in the event that brakes were to fail, how far would the car compress the emergency safety spring? So here's that emergency safety spring right there. And so then basically, you know, what energy did we start off with? This EGI. And then all of this EGI right here at the top is going to be equal to all of this elastic energy at the bottom, which is also equal to all of this kinetic and gravitational energy in the middle. So all of these energies are equal to each other, and so we can find how much elastic energy there is in that spring when it's compressed, and then we can figure out how far it has been compressed, because we know that elastic energy is equal to 1/2 k, which is the spring constant, times x squared. And then last is acceleration, and so you're trying to find acceleration, and this is where you can use one of your kinematic equations. So way back in Unit 3, when we learned about acceleration, you can use your kinematic equations. So it's going to be one of those 4, and I'll let you try to figure that out. So, so you figure out how much the velocity changed when the car hits the spring. So the car has kinetic energy before it hits the spring at the bottom, and that all turns into elastic energy that you figured out in number 5. All right, so I think I've kind of got you started on everything. I hope this isn't too confusing. And yeah, hopefully it's helpful. If it's not, just try to do your best with these problems from Worksheet 2. All right, good luck with everything.